And we've already talked about these inflection points, but we'll do it formally now. An inflection point is where we change concavity. We call something concave up. Think happy. If it's curved like a parabola going up. And concave down, if it's like a parabola going down. Now, if something is concave up, and we drew a bunch of tangents on there, can you see that wherever you draw those tangents, the curve is above those tangents? The tangents are always going to be below the curve. That's what happens when something is curved concave up. Vice versa, if you took a whole bunch of points on a concave down and drew tangents, the tangents would always be above the curve. The curve would always be underneath its tangents. So I would say, let's take out two colors of pens here. Let's do concave up, positive stuff in blue, and concave down, negative stuff in red. So here, the graph is concave up. Here it's concave up. Here it's concave up. And in these sections, it's concave down. I like talking about this point right there. That's an interesting point. That's an interesting point because if we talk about this graph is continuous at that point. And remember, we would say that something is continuous. Our unofficial definition is if you can draw the graph without lifting your pencil, the graph is continuous. If you had to lift it and jump to another spot, or if there was a hole that you're like, oh, I gotta hop to the other side of this hole, that's a point of discontinuity. Then you have something discontinuous. This is interesting because even though this graph would be continuous for the whole thing, there is a non-permissible value for your derivative at this point. And the reason there would be a non-permissible value for your derivative at that point is if something is allowed, in other words, not a non-permissible value, then like right here at Q, I can find a tangent and I can find its slope. But the problem at this point right here, I could draw a tangent here, I could draw another tangent that way, I could draw a tangent. There'd be like a million, an infinite amount of possible tangents that could all teeter-totter on there. You can imagine in just a line, you'd be like, I can rotate this line on that point and have more than one value. And in mathematics, whenever something has like lots of values, instead of saying, these are the lots of values we're allowing, we're just saying, no, 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 it's just not allowed. We would like one answer or have it not allowed. So at this point, we would have a non-permissible value for our derivative, even though our original function had all values through it. Okay. So P, Q, and R on there, where it changes concavity, we call those inflection points. And we've been introduced to the stationary point of inflection, but regular inflection points are just changing from concave up to concave down or vice versa. And I've already talked about it, but the second derivative, this is maybe, I'm going to take this word here, test for, let's stroke that out, and just change it to find. Because there is a second derivative test that has nothing to do with concavity. But everybody thinks like, we will use the second derivative 99% of the time for concavity. Then there's a second derivative test we're going to learn that we are never, ever, hardly ever going to use except for like one question on your test. And it finds maximums and minimums. So I'm trying really hard to take away the word test for concavity. Let's just find concavity with the second derivative, because the second derivative test is its own special thing that we're going to learn later. Okay, so some things we know. The second derivative is the rate of change of the first derivative. Rate of change is a derivative. So a derivative of something is always the rate of change of whatever was right above it. So the first derivative is the rate of change of the regular function. The second derivative is the rate of change of the first derivative. So if we notice that our first derivatives are increasing, that makes the shape concave up. If our first derivatives, anytime they're increasing, even if they started negative here, then went to 0, then went to positive, like a parabola, this would all be concave up. So how do we tell if, then this is a sort of a connection between what we were doing already, okay? What have we done up till now? Up till now, we had done the first derivative, you remember, and done this first derivative and put our critical points on there and found out where our graph was increasing and decreasing. Now, if you went to your second derivative and found a critical point on your second derivative and found out where something was increasing and decreasing, this increasing and decreasing would be telling you about the first derivative. And if something is increasing, we just noticed that that translates to the original graph to be concave up. And here's where understanding calculus can get confusing, because you have to understand, if I plug something into my second derivative and it's positive, it tells me my tangents are increasing. Because going one level up is always about increasing and decreasing. Going two levels up, we now just notice that if your tangents are increasing, that makes something concave up. And in the next section, we're going to find out if your tangents are decreasing, that makes something concave down. So this is the understanding part. The simplistic part of it is your second derivative. If it's positive, you will find out your original graph is concave up. If it's negative, it tells you your original graph is concave down. So same thing with all of these concave down ones. We would notice that our tangents are decreasing. They're getting smaller. That makes it concave down. You have to use the word attest. Oh, I don't want to. But your test for concavity, what would be a good, oh, we're getting English. We already wrote an essay on inflection points today. Now we're looking for a good synonym for test for concavity. The check for concavity. So, if it is positive, And you're going to see me use this notation a ton. Positive sign makes me happy, I smile. I draw a smiley cyclops with a plus I. Negative, sad, that's a teardrop. Concave down. So there will be a point of inflection at any point where the second derivative changes sign, and this is 1, second derivative changes sign, and 2, the second derivative is equal to 0. Because again, you could have a non-permissible value and not have an inflection point. So just like maxes and mins needing 2 reasons, inflection points need the 2 reasons as well. And we often forget this second one because 99.9% of your examples don't involve non-permissible values. So when we get to that one example where I add a non-permissible value, everybody forgets. So I don't even know why I should remind you, because even if I remind you, you're all going to forget. Right? I prefer, so the 2 things that you need. 1, you need that the second derivative is equal to 0 at that point. And in number 2, you have 2 choices. You have either to show, and this is the one that I like the most, if it changes from concave up to concave down, it feels like pretty obvious that it's an inflection point. Less intuitive is this. If your second derivative is equal to 0, and your first derivative it never grows old. It's so enjoyable every Tuesday. And it's always the best. Because it's always the students that are actually coming late for their regular class time. They come in so fast. Yeah, it's just... Okay. So, if the first derivative doesn't change sign, and the second derivative is equal to 0, that one I feel you really have to think about a long time to make it make sense to you. So I think you will like what I've underlined in the green as your second reason better. Because I think it makes more sense intuitively. If you know that it changed from concave up to concave down, and your second derivative is 0, perfect. That's an inflection. But it could also be that your first derivative, if it stayed positive, that your function, so what we have is we have the second derivative equal to 0 at this point, and my function is staying positive. The only way this can be an inflection point right? If your first derivative changed from positive to negative, well, then it would be a minimum or a maximum. But if we have an inflection point there, and the other one, or if we have that the second derivative is equal to 0, and your first derivative stays increasing, okay? It's impossible to keep it, if I even try it, if I start concave down, and I hit this point, and I want to stay concave down, but keep going up, well, either I end up with something, you can't draw it. So that's the part that's underlined in blue. Again, I'm not too worried about that, understanding that one as much, you'll probably use the green more often, but it is worth thinking about. So here we have the graph that we were looking at before, and it says, yeah, this is exactly the one that we just finished. So why don't we, instead of in our notes, let's just make a note that we're going to go back and see our previous graph, which we had right here. We've already done all of this work, but we hadn't found this point. So if we go back to this point now, what would we do? We would have found our first derivative, which we did already. We would have done all of this work, and now we're going to find our second derivative. So we would take our first derivative, 12x squared minus 24x. Factor that out. Common factor of 12x. So we would have made our number line, and now we would know that this second value on our number line should have been a 2. And just to double check, if you plug in something less than 0, this factor would be negative, this factor would be negative. So just confirming that that section would be positive and concave up. If I plug something between 0 and 2, like 1, this factor is positive, this one's still negative. And finally, both of them would be positive for anything bigger than 2. So as far as the question was to show that it has an inflection point, okay? So we would say, as far as showing that, since f double prime of 2 equals 0, that's our reason number 1. And reason number 2, the graph changes from concave down to concave up. So again, if a question says, show that it has a point of inflection, okay, you'd have all of that work from that previous graph. You'd find your first derivative, you'd find your second derivative, you'd have your number lines, and then you would have to show the two things. Second derivative is equal to 0, and this one changed from concave down to concave up. That's enough information to say that it is an inflection point. So I would like you to take the next example on your own and graph it completely. First derivative test and first derivative test and, oh, I shouldn't say it that way. Do your first derivative and do your second derivative. Find your maxes and mins. Find your inflection points. Draw a nice graph. Label everything. All right, let's see how you did. So preliminaries, we could find our y-intercept. X-intercepts don't look like they would be easy to find here. Find our first derivative, set it equal to 0, and find our critical points. Our stationary points are at 3 and negative 1. Here's our number line for our derivative. And again, I like to label this number line. Wow. I like to label this number line with our derivative to remind us that that's where we plug numbers into. Because you're plugging numbers into all sorts of things. So I'm going to plug in values into my factored form, and I find out increasing, decreasing, increasing, which tells me that those are maxes and mins. Because I had no non-permissible values. All of my values there were where the derivative was equal to 0. And I would find the y-coordinate of those points by plugging into my original equation. Next, I'd go to my second derivative to find inflection points. Set it equal to 0 and solve. The only place it's equal to 0 is at x equals 1. Draw my number line for my second derivative. Before 1 it's negative, after 1 it's positive, and we get that inflection point, and there's your graph.